hope that I will see you tomorrow on the cruise on the Volga River. It is a beautiful place, and I was told by the organizer that the weather is guaranteed. It is reserved for us, okay? So I welcome you also for the cruise on Volga River. And today I would please welcome our first speaker, the distinguished professor, I checked how the pronunciation, Sergei Sajin. He is from the University of Brighton in United Kingdom, and his major fields of scientific research is numerical and asymptotic modeling of fluid dynamics, heat mass transfer, and combustion processes in diesel and gasoline sprays. And today's talk is on modeling of sprays, simple solutions to complex problems. Please welcome.
Thank you very much for your very kind introduction, and thank you everybody for attending my talk. So I will try to do my best not to disappoint you. Sorry, could you just regulate a little bit because it resonates? Can you regulate it? Fine, thank you. And what I will do, I will share with you some of our recent results, focus on the modeling of sprays. But my main focus will be not on modeling of particular phenomena, but rather sharing with you my philosophy of modeling, or my general approach to modeling, which can have a much wider range of applications compared with what I'm going to show to you today. And now I will try to, so this is the plan of my presentation. I will start with the background, and then I will focus on three specific problems. First is modeling of drying droplets, then modeling of suspended droplets, then microexplosions. And then, if time permitting, then I will give you a very brief overview of other developments in the field. And I will start with the background. So this is an overview of activities of our laboratory. So we are primarily interested in study of internal combustion engines. So that means that we don't develop engines themselves, but we develop tools which allow engineers to develop most efficient and least pollutant engines. So as you can see, there is a wide range of activities going on, and I'm involved mainly in the activity which is related to sprays. And this is something that is encircled here. So that means that my focus will be primarily on automotive sprays. But the tools which was developed for automotive sprays are very similar and sometimes identical to the tools which are applicable to modeling other classes of sprays. For example, sprays in turbines, sprays in pharmaceutical applications, sprays in environment, and I could continue this list. And as you know, it is my first presentation. It is not my first presentation here. And last year, I gave a lecture with a rather similar title. So the beginning was exactly the same as for the current lecture, but the second part was a little bit different. And this was the plan of my last year lecture. So I started with the background and then considered Lagrangian approach and full Lagrangian approach, spherical, non-spherical droplets, and then heating and evaporation and ignition. And I assume that many of you attended my last year lecture, and I tried to do my best to avoid overlap between what was covered last year and what I'm going to cover today, except perhaps the background. The background will be rather similar as as to the background, what we're interested primarily in droplets, because spray consists of droplets. And in contrast to most of models which are published in the literature and available in commercial CFD codes, we take into account the temperature gradient inside the droplets. And also, in contrast to most of research in this area, we considered the effect of thermal radiation as a volumetric effect. So that means that we take into account the volumetric heating of droplets by thermal radiation, and this is taken into account by this term, And also, we apply this equation, which is spherical symmetry of droplets, not only to the stationary droplets, but also to the moving droplets. And this is done by introducing the so-called effective thermal conductivity. And this effective thermal conductivity is linked with the liquid thermal conductivity by this simple formula. I'm not going to go any further here because that is something that I discussed many times in the previous presentations. And I will move to another equation which is widely used in our modeling. This is the equation for species diffusion. So the droplets which we're dealing with are multi-component. So there is no automotive fuel which consists of a single component. And this leads us to the problem of species diffusion inside the droplet. This species diffusion is described by the species diffusion equation. And the species diffusion equation, again, is presented for spherical symmetrical case, but it can be applied for the case of moving droplets by introducing the so-called effective diffusivity model, in which the effective diffusivity of species is linked with the liquid diffusivity by this simple equation. And then the problem with the applications of this equation is that all these models were implemented into computation fluid dynamics codes, and this is one of our recent publications on this subject. And the problem is that when we deal with automotive fuels, the number of components appears to be significant. It could exceed 100 components. And in this case, solving equations for each component would be a bit time-consuming. And to deal with this sort of problem, and this is the composition of realistic diesel fuel, we developed the so-called multi-dimensional quasi-discrete model, in which the groups of components were replaced by the so-called quasi-components. Quasi-components are not the real components which you can touch, which exists, but at the same time there are some sort of a ghost components. But these ghost components appears to bring some sort of a real benefits of to modeling. This is something that I covered more or less last year. And I'm not going to consider it in any further details here. And now I'm going to move to specific problems, and I will start with droplet drawing. So droplet drawing is a classical problem in many applications. For example, in pharmacy, when we produce a powder with a drug, then we need to dissolve a certain drug first, and then dry the spray, and as a result you got the powder like this, the powder like this. Then the problem is how to model this drying process. You have a lot of particles, which are moving inside the droplets, and then the surface of the droplets evaporates. So you can try to trace, for example, trajectories of individual particles, but you can do this, but this approach would be rather complex. Instead, we suggested a different approach. So these particles can be, these ensemble of particles can be treated as non-evaporating fluids. And as a result, the mixture of particles and water, distilled water, can be considered as a mixture of two fluids, two liquids, one evaporating liquid and one non-evaporating liquid. And here we have the formulation of the problem. We have a Chisasan, which is dissolved in water, and the mass fraction of Chisasan is 0.4%, and the mass fraction of water is 99.6%. And so these are initial conditions for ambient air for Chisasan, and these are the properties of Chisasan. And then, once we made this assumption, then we are on the track on the model which was developed for completely different problems. The model which was developed for automotive fuels. This has nothing to do with automotive fuels. And we use the same equation for species diffusion, which was shown in the background. And then this equation can be solved numerically, and this is something that was done in several papers. But in our case, it was solved analytically. And this is the analytical solution to this equation. And I'm not going to show the details because it would be a bit irrelevant for the main message of my presentation. So these are, at the boundary, we assume that liquid is, the water is the only evaporating substance, and Chisasan is not evaporating at all. And then we use the so-called Raoult's law at the surface for the evaporating water. And then, once we have solved this problem, then we can get the time evolution of droplet radii and the time evolution of mass fraction of water and mass fraction of Chisasan. And we cannot really validate rigorously all these plots which are shown here. But what we can validate is the typical time of evaporation of the droplets. And typical time of the evaporation of the droplets is about 0.12 seconds, is compatible with the experimental observations. And these results were published last year in our paper, prepared together with a colleague from Department of Pharmacy at our university, and also the colleagues from Kazan University in Russia, not far from here. And now I'm going to move to another topic, which focuses on suspended droplets. And this is the motivation of this work. That is our colleagues at Tomsk University. It is a little bit too further on to Siberia. Performed a number of experiments in which the droplets were suspended on a metal rod. And then the temperature of the hold of the rod increases with time, as it is shown here, depending on the temperature of the ambient air. Now we had an observation, the technique, the experimental technique which they could use, allowed them to estimate the temperature distribution inside the droplet. And here you see some typical profiles at various cross sections and at various time instants. And the same distribution is presented on these plots, where we have the actual plots of the temperature inside the droplets versus the distance from the droplet center, And now the problem is how to model these phenomena, because these phenomena appears to be quite complex. You have a complex connection between the droplets and the rod. And it looks as if we are almost bound to perform a three-dimensional modeling of the phenomenon, which would be very time-consuming. And I would question the need of these sort of developments. So what we did, we tried to solve this problem, but using a different approach, using a simple approach. So what we did, we based our analysis on the heat transfer equation inside the droplet, including the radiation term. This radiation term takes into account the volumetric, in the general case, it takes into account the volumetric absorption of thermal radiation inside the droplet. But at the same time, you need to stretch your imagination that the same equation could be applied to any other means of volumetric heating of the droplets, not necessarily thermal radiation. And these other means could be heating via the transfer of heat through the rod. And then once we have made this assumption, then our task would be to calculate the amount of heat which is transferred through the rod to the droplet. And then once we calculated this amount of heat transferred through the rod to the droplet, then we would be able to calculate the value of the source term. So this is the underlying philosophy. All the rest is just a bit of calculations. So what we did, we used the analytical solution to this equation, including the source term. The nature of the source term at this stage is not specified. We will specify it a little bit later. And the analytical solution is presented here. This is the equation, and this is the analytical solution. And here, this term takes into account the effect of thermal radiation. But for me, at the moment, is not necessarily thermal radiation. It is whatever means of internal heating of the droplet. And now we are going to estimate, this sort of level of heating of the droplet, but not by the thermal radiation, but by means of transfer of heat by conduction through the rod. And then we solve a very, very simple problem. Very simple problem. We have the cross-sectional area of the contact between droplet and the rod. We have the temperature at the center of the droplet. We have the temperature of support, or the temperature of the rod. We have average radius of the rod. And then we have the thermal conductivity of water. It's a very simple formula. You can find it in in a manual for undergraduate students. And then we can make another assumption, is that this heat is, strictly speaking, it will be distributed inside the droplet. But inside the droplet, you have a lot of convective processes. If not the forced convection, then it could be a natural convection. And these convective processes lead to the mixing of various layers inside the droplet. And then when this mixing takes place, then we can replace this heat transfer to the droplet to heat supplies to the unit volume of the droplet. So we assume that this heat supply to the droplet is uniformly distributed inside the droplet. It is uniformly distributed inside the droplet. And then once we have obtained this heat uniformly distributed inside the droplet, then mathematically this heat can be replaced by this source term in a heat conduction equation. The source term in heat conduction equation. So as you can see, we use the equation which was originally designed to take into account the effect of thermal radiation on heating of droplets, but applied to the case of the droplet, which is heated via the rod. And then once we have done this, then we can get the plots of temperature versus distance from the center of the droplet. And we have, with a reasonable deviation between the results, reasonable agreement with experimental data. And these results were published in our joint paper with the colleagues from Tomsk University, and it was published last year. And now we are going to move to the last problem, the last topic of the presentation, which is focused on microexplosions. So perhaps not many of you know that to improve the performance of internal combustion engines, people tend to add water into the fuel, water in diesel fuel. It looks bizarre, but at the same time, it produces a very interesting effect, that water dissolved in fuel forms some sort of subdroplets inside fuel droplets. Now, the boiling temperature of water is well below the boiling temperature of most components of diesel fuel. And as a result, when the diesel fuel with water subdroplets is injected into the hot chamber, in a diesel engine chamber, then they are heated, and when the droplet temperature, when subdroplet temperature reaches the boiling point of water, then they explode. And when they explode, then a big fuel droplet turns into a number of very small subdroplets, very small aerosols, which evaporate very quickly, and this improves the performance of the engine. So this is the underlying philosophy behind the microexplosions. There are a number of other reasons for this, but this is something that I'm not going to discuss today. And this is a typical video of what is going on during microexplosions. And then we can have a closer look at a sequence of photographs, which can give you a bit of a clearer view of what is going on with the microexplosions. As you can see here, you can see some sort of a small subdroplets in the fuel droplet, and then these subdroplets start increasing, and eventually everything explodes. Everything explodes here. And now, this is the reproduction. This is the reproduction of the pictures which are shown by my colleagues from the group and the group in the University of Malaysia. And please note that seconds here need to be replaced by milliseconds. Now the problem is how to model this phenomena. And the interest in modeling this phenomena is, was quite substantial. And a number of groups, including the group in our university, in the University of Brunel, together with a research fellow from Japan, they developed a very sophisticated model based on direct numerical simulation of all the processes inside the droplet. They try to trace all these interfaces between the water and the fuel and air, and produced quite impressive results. Here you can see quite impressive results, and which show the evolution, the detailed evolution of these water subdroplets inside the fuel droplet. And clearly, it is, so everybody, including me, were quite impressed when we saw these pictures. But the problem is that these pictures were obtained for very specific initial and boundary conditions. When you change these initial and boundary conditions even slightly, then the whole picture will be different. And this brings us to a point where we need to decide how exactly we are going to use these sort of pictures for engineering applications. For the engineering applications, we don't really need to know all these, each and every of these details. What we need to know is that where the explosion will take place and when exactly, what is the typical time delay between the injection of the spray and the time of microexplosion. So, and this led us to not to try to compete with this group and try to develop some sort of a more sophisticated direct numerical simulation model, but try to approach to the problem from a completely different perspective. So what we did, we developed a very simple model. So we considered that a water subdroplet of a radius of RW is located in the center of a big fuel droplet of radius RD. Then the temperature at the interface between water and fuel is TW, and the temperature at the surface of the fuel droplet is TS. And then we return to the same heat conduction equation inside the droplet. In the general case, we use this source term due to thermal radiation, but eventually, we are not going to, we're going to assume that this term is equal to 0, okay? And then in this equation, what we did, we took into account the existence of two layers, that is the layer of water and the layer of fuel. And also in the general case, we took into account the difference between the distribution of temperature in the water and temperature in the fuel. And also we use a set of boundary conditions at the interface between water and fuel, and also a typical boundary condition at the surface of the droplet. And then these boundary conditions at the surface of the droplet were simplified. So at this stage, when we wanted to use to make some sort of first steps, some sort of preliminary results in the modeling, then we eventually replace these general Robin boundary condition by a simple Dirichlet boundary condition. We managed to justify, this sort of simplification. It's a bit of a crude assumption, but at the same time, this assumption is workable. And then we made a long list of assumptions. One of the assumptions, the first assumption was that we assume that the temperature at the surface of the droplet is fixed and it doesn't change with time. Then we assume that effects of droplet heating and effect of swelling and evaporation can be ignored. And obviously, during the time of microexplosion, that these swelling and evaporation are relatively small. And then we can assume that initially the distribution of temperature inside the droplet doesn't depend on the distance from the center of the droplet. And then the effect of the source term is taken into account initially, but eventually it was ignored. And once we made these assumptions, then the analytical solution to this equation turns out to be particularly simple. So it is shown here, and this is the meaning of the term, and the meaning of other terms is presented here. So it is, there are a lot of symbols, but at the same time, the structure of the solution is not particularly complex. And then, once we reached the solution, then we applied it to a particular experiment, which was performed in a group at the University of Petronas in Malaysia. And these are input parameters for the droplets, which were supplied by my colleagues working at that university. And as a result, using this solution, we were able to describe the heating of the droplet with time. So, for example, initially we had a jump in temperature between the droplet and the ambient air, and then we have a gradual spread of heat inside the droplet. And this leads to the gradual increase of temperature at the interface between the water and the fuel. And eventually, at some stage, that is time instant 5, we have this temperature at the interface between water and fuel reaches the water boiling point. And we assume that at this stage we have microexplosion. Strictly speaking, it will be puffing, which leads to microexplosions. And once we have prepared a number of curves like this, we were able to plot the time to puffing or time to microexplosion for different values of surface temperature and different values of the initial droplet temperature on this graph. This is the initial droplet diameter, and these are the values of time to puffing, which is assumed to be equal to the time to microexplosion, and as a function of the initial droplet diameter. And on this plot, on the same plot, we put the experimental results. And clearly, we couldn't get, one-to-one correspondence between experimental and modeling results. But at the same time, we have a correct order of magnitude. And also, we were able to show that our model at least predicts the minimal value of the delay time. And this minimal value of time to puffing is due to the fact that we didn't take into account the initial heating of the droplet, but we assume that the temperature of the droplet immediately reaches almost the boiling point. And then these results were published in the paper in the International Journal of Heat and Mass Transfer early this year. And these include our co-authors from the University of Petronas. And then I will just summarize briefly some other developments in the field. So so one of the directions on which we are working very closely with this university is focused on the development of new mathematical tools for modeling of spray, ignition, and combustion. So the expertise in this field lies actually not in our group, but mainly in the group of Professor Sobolev, and this is our most recent paper on this subject, which is published in the Journal Engineering Mathematics early this year. And then, another direction of research is focused on modeling of blended fuel, heating and evaporation, using previously developed theoretical tools. And this paper was prepared by my former research students, and then a research student of my former research student. And we just build it up, and we build it up this model on our previous model, and it is essentially focused on the refinement of the previously developed model. And then another direction of research is focused on further development of the full Lagrangian approach, and which was described the last year. And we added new models, new submodels into these approach, and then it was implemented into computational fluid dynamics codes fluent. Then we tried to generalize our previously developed model when taking into account the activity coefficient during the evaporation process. And then much of our research is focused on the modeling of vortex rings inside the engines. That is something that we regularly observe, and we try to develop relatively simple models of the phenomena. And this work is mainly performed in collaboration with our colleagues from Rouen University and also from Estonia. And our future plans is to incorporate multi-phase flows into this model. And I would like to thank IPSRC and other groups for supporting of our research. And thank you very much for your attention. And I think that I kept well in time.
That's your time, so thanks for keeping your time. I left 5 minutes for questions.
Yep.
Any questions? So I understand, yeah, it was clear presentation.
Yeah,
yeah, but even for computer scientists. But we have one question, and if anyone else wish, please, we have multiple microphones. If the next question we have, please pick up one of those microphones. Go ahead.
The question is about droplet evaporation speed.
Sorry?
Question about droplet evaporation speed.
Yes.
Droplet evaporation speed depends not only on diffusion of components inside the droplets,
yeah,
but even of convection and diffusion of components outside the droplets in the outer gases. How did you solve this problem?
Okay. We didn't solve the problem, but we used a solution developed by other groups. So I didn't want to deliver a lecture, a comprehensive modeling of droplet heating and evaporation, considering both effects in the liquid phase and in the gas phase. So this would need a separate lecture. And what I did, I focused on the results which were specifically obtained in our group. So you're absolutely right that there are processes in the gas phase which we took into account in the modeling. I wouldn't be able to give you a very short answer to this, but my short answer is that we use a previously developed model, and there is no development from our side here.
Okay,
have I answered my question?
Yes.
Okay.
Any other question? If no question, thank you very much again for a very interesting presentation. And I'm pleased to welcome the second speaker of our session. That's Professor Yashar Azizian Kalandarach from the University of Mogagheh, Ardabili, correctly pronounced, or close. And he is a distinguished professor in the area of nanotechnology, structured light, optics, of semiconductor nanostructure, diffractive optics. And his title of the presentation is Structured Light and its Application in Microscopy and Optical Trapping. We are setting up his presentation, so Professor Azizian, if you can tell a few words about your university, it would be great as well, because most don't know probably that region where you do research. Thank you very much.
Okay, it's my great pleasure to be here at the beautiful city of Samara and the University of Samara. At first, I would like to thank to the organizing committee and scientific committee of the conference, especially to Professor Viktor Soifer and Professor Svetlana Khunina for their invitation. And also I want to thank the organizing committee for their warm hospitalities. So yesterday I was changed some of my slides because I have found here some people from data sciences and computer sciences and also nanotechnology. But today I want to talk about the structured light and structured electron especially. At first I want to introduce my group and my city. I'm from Iran, from Ardabil city, a city in the north of Iran, from University of Muhaqqiq Ardebili, from the Sabalan University College of Namin, UMA. These are my students at our laboratory. Today, I want to start a talk about the history of light, and also I want to conclude about the importance of light in our life. It's a very interesting diagram about the light from beginning of the universe to the formation of the beginning of the universe, the Big Bang Theory 14 billion years ago, and then formation of planets, stars, and then genesis of the humans and ourselves. We all know, for example, for 4.5 billion years ago, the birth of the Earth, 2.4 billion years ago, the genesis of the single cells, and 2 million years ago, the genesis of the human. After the genesis of the human, the early bird human, and from these intelligent humans, the light was in the center of the process. This is very important. There are some discoveries with archaeologists, which the applications of the light in very ancient time, for example, in Chocotin cave in China, and also in Lascaux cave in France 17 years ago. They have found some devices which used light. People used light in ancient time to making painting in dark places. This is an MP3 version of my presentation, which shows the applications of light and importance of light from 3,000 years BC, fabrication of candle glasses Egypt, observation of comets, stars in Chinese by Chinese astronomers and Babylonians, recording the first eclipse to build the first observatory for astronomers. Then, after that, by the history, this is the story of the light, which peoples, by the entering the science and philosophy to the humans world, some famous philosophers, all famous philosophers talks about light. And then also in Islamic age, we have some Iranian scientists which works about the lights. One of the most important person was Ibn al-Haytham or al-Hazan, who worked experimentally and theoretically about the light. The first photograph was made by Ibn al-Haytham. He was the founder of the some theories about the fundamental phenomena of optics. And also, after Islamic short golden age, some other people from Europe, you are all familiar with these scientists, Johannes Kepler, Galileo, and also after 20th century, Isaac Newton, who was the first introduced the particle properties of light, and Christian Huygens, the wave properties of light. And then in the 19th century, Thomas Young, Maxwell, and to Niels Bohr, to Albert Einstein. These scientists works directly on the light. I skipped this because this is very special slide. So I gathered here the name of some people, the name of Nobel laureates, or directly connected with light. I estimated approximately 65% of Nobel laureates of physics get Nobel Prize, which directly connected with light. From the first one, Röntgen in 1909, to 3 slides. This is one. Second slide, the people by Nobel laureates of light, and the last one was 3 persons who Arthur Ashkin, Gerard Moreau, and Donna Strickland in 2018, who was directly connected with light, which they are get the Nobel Prize about the fascinating area of the optical tweezers and optical manipulations. So I think this is sufficient for proving that light is important. But imagine life without light. Without light, imagine this room without life. It will be impossible because the vision is connected with light, the photosynthesis is connected directly with light, the generation of vitamin D and also adjustment of calcium in our body is directly connected with light, and also the food and energy topics. Yesterday, 2 great professors, Professor Hayashi and also Professor Nikitov, talks about 2 important quasi-particles. One of them plasmons, and the second one was about the magnons. Today I want to again talk about quasi-particles of physics, but today is about photons and electrons. We are all familiar with photons and electrons. These are very important in the point of physics, important quasi-particles which are working with this, which our world works with these 2 important quasi-particles. This slide is a comparison between 2 important quasi-particles, which as I said, the first one is electron. Electrons have rest mass and charge, spin 1 divided by 2, and also photons have no mass, no charge with spin 1. Spin 1 is a interesting story, but today I am not going to talk about that. But the energy of the photon is the visible energy of the photon is about 500 nanometer, and the energy of the electron is about this is the resolution differences between same objects which have gotten by electron microscope and also photon microscopes works with photons. So for understanding the structure of these important quasi-particles, it's important to know about the degree of freedoms which we should be familiar with them. In the case of light, in the case of photon, 4 degrees of freedoms are important. The first one is color or energy. The second one is polarization, which Professor Nikitov yesterday talked about, the spin up and spin down. And third one we are interested with it, the orbital angular momentum of light. And the fourth one, the radial mode or the intensity of the light, the quality of light and the quantity of the light. And this, in the case of electrons also, this is basic things I think we all physicists are familiar with. In the case of free electrons, with considering no relativistic regime, no polarization regime, if we have free electron, we can solve the Schrödinger equation for the free electrons. We will receive the Helmholtz equation. The Helmholtz equation here by solving the Helmholtz equation in different, for example, cylindrical coordinates or spherical coordinates, we have the answers: plane waves, Bessel waves, Mathieu waves, and so on, the superposition of these waves. In the case of the free electrons which traveling in the propagated in the direction of Z, we have by using the Schrödinger equation, we have a wave, a quantum state, this wave state, which by putting this wave state, by solving this wave state, we have this equation. This equation are familiar with the physicists which works in the field of optics. What's the name of the equation? It's the Paraxial Log Equation, yes. By solving these paraxial equations, we have the Laguerre-Gaussian mode, Hermite-Gaussian mode, orthogonal and complete modes, and the superposition of these modes. So this is color, the first degree of freedom, polarization, the horizontal and vertical, and also two types of. There are some devices which we can change the polarization: quarter wave plate, half wave plate, and also angular momentum. This is very important because then I talked about the Nobel Prize of 2018 by Arthur Ashkin. This is a laser pointer. Using this, we know all types of light have optical pressure. And optical pressure means is force. This is, I am applying force to this bench using this laser pointer, but I cannot push any movement on the bench using the laser pointer, because of the order of the force. The order of force, maybe for replacing this bench from one point to another point, we need maybe 100 Newton. But the order of the force which here we have in this laser pointer in the order of piconewton. But there are some objects, some micro objects which we can change fold, default, replaced from one point to another point, look like very small micro objects and nano objects, nanoparticles, biological proteins, viruses, microbes. We can manipulate using optical pressure. And the name of the device which people works, and we also in our laboratory works with the device, is optical tweezer. This is due to the orbital angular momentum of light. We can fabricate the orbital angular, different well-defined orbital angular momentum of light using phase diagram. This one is a fantastic picture, pasta fusili, which shows the orbital angular momentum from the Log Gaussian mode. So there are some other devices, for example, a spiral phase plate, which we can use using the spiral phase plates, the helical beams or vortex beams, orbital angular momentum. And this slide about the spin versus orbital angular momentum, this is clear here, spin angular momentum, and here we have orbital angular momentum. So what is the, and this is also other device, Q plate. Using Q plates, we can also change and fabricate orbital and well-defined orbital angular momentum for light. I'm skipping these slides, so due to the time. So what is the applications of structured light? We can, for example, this is just, this pointer have just Gaussian mode. We can change the mode of an orbital angular momentum of this Gaussian laser to different special, using the special functions of mathematics. Gaussian mode, Lager Gaussian, Hermite Gaussian mode, Bessel mode, parabolic mode, and so on. These are the applications of structured light and also structured electrons. The first one is in quantum computation, in optical microscopy, optical manipulation. I said about optical manipulation, which optical tweezer, and high-dimensional entanglements in data sciences, classical communication, and quantum cryptography. One of the most interesting devices which we can prepare, we can fabricate the well-defined orbital angular momentum for light, is spatial light modulator. There are some companies in all over the world to fabricate the spatial light modulator. This video projector generally is the spatial light modulator. We extracted the LCD of this video projector from and the LCD of all video projectors can apply as spatial light modulator. By generating mathematically and computationally the phase of the different lights, we can make and mix and with the superposition of different special functions, we can make a well-defined orbital angular momentum for light. And I want to talk about the history of the angular momentum and from the basics. If, for example, in this, the last slide was about the digital holography. Here we have, before the digital holography, we had, if you remember, these are our desire in our country 20 years ago to have a Zenith camera, the Russian Zenith camera. And I bought the Zenith camera, and using the camera, nowadays I fabricate some analog holograms. For example, by taking some picture from the screen of the computer, we can develop some gratings, some blaze gratings, some Rankine gratings, and then we can fabricate both amplitude and phase holograms. Using these holograms, we can have some structured lights. So I talked about the, this is a typical video simulation about the folding of DNA, biological object, which with this 1.3145 piconewton. I said that the structured light is used for folding and defolding some biological objects, which Arthur Ashkin's works about these objects. By optical manipulation, also these have some applications. So this is Laguerre-Gaussian mode. This is the formula of Laguerre-Gaussian mode. And in the nature, we have seen in the face of this hologram in the body of the zebra. And we can get this hologram using video projector from the phase of the Laguerre-Gaussian mode with the well-defined orbital angular momentum. So one of my interests, which I am one of the most important motivation which I am here today, to have a collaboration with the group of optics, computer optics of Samara University. I have reviewed the works of the great book of the Professor Seufer, and also the papers written by Professor Hunina and Professor Kotliar. And I have worked on the published papers in different journals. There was very great papers. And I'm trying to find some applications about the published papers, and in the field of optical microscopy, and also in the field of the optical manipulation or trapping of micro objects by the light. These are some simulation which, for example, in the case of Laguerre-Gaussian modes, we have some simulations and also experimental results, which, for example, this slide shows the superposition of 4 shifted Laguerre-Gaussian beams, who Professor Kotliar and Hunina published the paper in Physical Review A, and we have superposed 4 of these beams, and this is the interference of the superposition of 4 beams. These types of beams may be useful for trapping of small nanoparticles. Here is the analytical calculations we have. These are the simulations and also experimental results. This is amplitude, this is the phase. We engineered the different cases, and these are the experimental results. Also other parts here, we have the experimental results, phase, and also for different cases. Maybe these type of optical lights, optical manipulation, may be used for I said for trapping a particle, getting a particle, rotating the particle, and transferring particle from one point to other point. The second thing which we are interested at, and this is more interesting in quantum computation and entanglement, the self-healing properties of these beams. these non-diffracting beams have self-healing properties. For example, by applying any defect here, by propagating these types of light, we can see the self-healing properties of we are all familiar with self-healing properties of light, but here we quantified the self-healing properties. By propagating of light, we see the 93% self-healing with Z, 84. The quantification of the self-healing properties is more important. And also, these are also other works which have been done by Professor Hunina, which the self-healing properties of parabolic beams. We are, as you see, we can see the self-healing properties for fractionalized beams also here, and also these are the amplitude diagram of these beams. So I mentioned to the Laguerre-Gaussian beam. Laguerre-Gaussian is a well-defined beam structured light which have different applications. But one of the, unfortunately, this beam doesn't have self-healing properties. The self-healing property, this is not a good self-healing properties. Then we, in a work, we show that the superposition of two Laguerre-Gaussian beam can have good self-healing properties. But by the interference of two Laguerre-Gaussian beam, we analyze the self-healing properties of these materials. So the last thing which I want to talk about, that one of the most applications of the structured light is in optical microscopy. Optical microscopy, super resolution in fluorescence microscopy, and light sheet microscopy, 3D interferometric microscopy. Fabrication of a structured light, fabrication of very narrow structured light are applicable in these three fields. This is a setup which we have in our laboratory, mirror interferometric analysis. These are microchannels which we have prepared in our laboratory. These microchannels, we can analyze the microchannel 3D imaging using interferometric 3D microscopy. And also we have other applications for these techniques. Interferometry is important. Getting information from interferometric pattern are also important, because we didn't have, for example, by ordinary microscopy techniques, we didn't have any other information, but any other 3D information. But from interferometric pattern and phase analysis, and also using Fourier optics, we can get more information about the 3D micron-sized and nano-sized, and also nano-sized objects. It is, we all know it is not possible to see nano-objects using optical visible light. But there are some information which, for example, in our laboratory, we analyzed the red blood cells, morphology of the red blood cells using interferometric microscopy technique. Red blood cells have a donut shape, and we have found some disease look like, for example, the fatty bloods and the blood with sugar have changed the morphology of the red bloods, depending on the amount of fat inside the blood. So we can analyze the morphology changes in bloods in comparison with healthy blood, and get some more information in comparison with ordinary optical microscopy using the interferometric 3D microscopies. So these are the pictures. So in the last session, I have time. I said I think I have time. I said yesterday I changed the slides, and I want to start a different talk here about the nanotechnology. If some people, as I understand it, there are some people here are interested with nanosciences. My last branch was and PhD was about the nanoscience and nanotechnology. I want to show that here some simple techniques for preparation of nano. Because of some restrictions in our place, we didn't have any devices to prepare using, for example, MBE, molecular beam epitaxy, and etc. This is a very simple technique for preparation of nanoparticles inside polymeric matrix for applications, different applications for fabrication of devices, look like solar cells, sensors, gas sensors, and so on. For example, for preparation of semiconductor nanoparticles inside polymeric matrix, we can use a cationic solution here, an anionic solution. For example, 30 seconds we use the polymers inside the cation, and then rinsing for 3 times each of time 10 seconds, and then in anions, for example, cadmium ions react with sulfur ions here to prepare the cadmium sulfide nanoparticles. By changing, this is the first cycle. From here to here, we have first cycle. If we start to continue this process, the second cycle, the third cycle, fourth cycle, this is the growth mechanism of a semiconductor nanostructures inside the polymeric matrix. These are the results. These are the spectroscopic results. This wavelength and absorbance, transmittance. There are some interferometric pattern here. We can calculate the particle or film thicknesses using this interferometric pattern. And also we have here the film thicknesses using a cross-sectional scanning electron microscope. Then we calculated the band gap of the semiconductor using these techniques. This is the real materials, real polymer nanocomposite materials which we have prepared. 2 cycle, 4 cycle, 6 cycle, and 8 cycles of Sylar. By increasing the cycles of Sylar, the band gap are red shifted. In the case of the 2 cycles, we have very small nanoparticles inside the polymeric materials. And by growth mechanism, the band gap of the nanostructures, semiconductor nanostructures, shifted to the red region. This is the band gap of the nanoparticles, and for 4 cycles, the band gap of the nanoparticles inside the polymeric matrix for 2 cycles, and also we have redshift here. This method is a simple method to control the band gap. to control the band gap or band gap engineering. For example, in some devices we need a defined band gap. For example, in the case of solar cells, we need to engineer the band gap of the nanoparticles inside the polymer. This is very simple method to preparation. Then physicists are interested with the physics of this phenomena. This depends on the quantum confinement of charge carriers inside the polymer's pores. We all know about the particle in box. I have some theories here. For example, I show the models. The most famous theory is the band gap, or the energy is equal to the kinetic term and Coulomb term and so on, and spin orbit terms. And here other model which has hyperbolic band model. This is effective mass approximation model. We are modeled the obtained experimental results using these exist theoretical models. The green is effective mass approximation. It comes from the particle in box, general particle in box in quantum mechanics. Hyperbolic band model, green, and the experimental. These are our experiment, four cycles, are our experimental results which match with hyperbolic band model. And also the stars are the experimental results which we obtained from the literature. In the case of other materials, zinc sulfide materials, also we have checked these properties. And also we have some other experiments on the surface. Maybe it will be interesting for Professor Sajin, the wettability and contact angle measurements on different surfaces by changing the morphology of the surfaces and also the chemical components of the surfaces. We can change the contact angle. We can engineer the contact angle of the surfaces by different cycles of this method. And also we have other methods, other techniques which we can change. For example, by thermal annealing, by adding dopants, we can change the contact angle of the nanomaterials. These are some electron microscopy images from the surface of the samples, and also these are the atomic force microscopy pictures, images from the samples. So, thank you very much for your attention, and I am at your service if you have any question.
Thank you very much for Thank you very much for very interesting presentation. I didn't know that so much knowledge is about light already. So I think that we'll get some questions. Yes, please. If anyone has a question, please go to the microphone.
Okay. Thank you very much for your nice talk. My question a little bit general. You are using structured light, but unfortunately I couldn't catch why you are using structured light. Is it simply light wave propagating in different modes, or other thing? What is the meaning of structured?
Okay. We have ordinary light. Yes. This is my idea, maybe here in front of some professors which works on the field of the structure. In my view, we have, for example, light from the sun. This is ordinary light from the in this room. These are all ordinary light with complex properties, with with different polarization, with different wavelengths. For example, in the case of laser, this is just Gaussian mode, have Gaussian mode. If we draw the intensity profile of this laser beam, this is Gaussian, this will be Gaussian. And we can change the structure of this Gaussian mode to other structures with well-defined force, well-defined optical pressure. This is the mean of the structured light. Okay.
Can I ask one more question? Okay, because you, at the beginning, you presented a lot of history of light, and you included history of light, and you mentioned there are a lot of work done by Arabic scientists, but you didn't spend a lot of time, and so I believe it's a good chance, because I don't know very well what kind of works have been done in Arabic countries. So if you go back to your slide, and if you choose one or two examples which gives us the idea of excellent work in Arabic countries.
Mm-hmm. Okay, thank you for your comments.
If you show now, or
show
just
the
one or
work.
two examples. Please give me just one or two examples of
yes.
work done by Arabic scientists.
Yeah. I don't have in a slide, but there are in literature. For example, I said one the Arabic, not just Arabic. It will be from Iran in general.
Iran.
Yes, because for example, Ibn al-Haytham was from Basra. Basra is a city in Iraq, just now, but at that time it was a part of Iran. And one of the works which worked by Al-Hazen, the fabrication of photographs. The first photograph was fabricated by Al-Hazen. Here I don't have the photograph. If you can search on literature, you can find the first photograph. The year of 2015 was the year of light, as you know. In honor to the Ibn al-Haytham, the UNESCO called this year as the year of light.
Okay, I have a lot of questions about quantum size effect, but we will discuss later.
Okay.
Thank you very much.
Okay, we will discuss now.
Any other questions? No questions, so I would like to thank you again very much for the presentation. And please join me in welcoming the last